Hello friends, welcome back. So in last video we finished here and then I said we need to see about the layer stack, and as a physical design engineer layer stacks are very important. Anytime you're gonna design like physical design, you might be having many different type of PDK. Some PDK might be coming from TSMC, something coming from Samsung. Inside a foundry also there are different process nodes, right? For example 14 nanometer, 10 nanometer. So for each process node, the PDK content will keep on changing, and the PDK is like a package. It will have all the definition of your devices, anything you are gonna use in your design, right? And also the document containing the design rule, how you gonna design them, what are the DRCs, everything. So for us, we have only one PDK, and that is sky130. So we need to have a very detailed look to our sky130 130, so that in future when we're gonna do any complex design, that time those DRCs, those unseen rule won't hunt us back, right? So that's why today's video is very important, because from today's video you will get a hint how to approach any PDK document. And in future if you're gonna pursue a physical design engineer role, then this is very important. In interview, if you tell your interviewer that hey, you know how to study PDK, the PDK documents, it will be a huge edge over other students. So to see about sky130 130, we have a dedicated website for that. So we'll just type sky130 and the first link. I'll give the link in the description. There are many things are there, and most of them are not working because they are still working on it, and we can also help them, like you can contribute, but this is for some other day. So for now we need to see what are the design rules, right? So we will go to design rules. Inside design rules there are many things. I will go through all of them, not all of them which are necessary today, but first we want to see the layer stacks. So layer stack will come under this criteria and assumptions, go inside, and process stack diagram. So this is your process stack diagram. If you are seeing it for the first time, you might be very puzzled, as I were when I saw, not this one, when I was working for my major project. That time only I first saw any PDK document in my MTech first year. So if you are seeing this thing before that, you are doing great than me, so don't worry. So see, in any process actually we have different type of metals, like this probably metal 1, let me change the color, this probably metal 2, and so on. And why we need those metal, like multiple metals? Because for example we have a design like this, and in this design we already have used our metal 1 for something, for some connection. In the same location, if we gonna do some other connection for some other block, then we can't use that same metal, right? It will be shorted. If I give you an analogy, for example, you have a highway, right? And that highway is congested. So that time what do we do generally? We build a flyover above it. So we have a flyover, there traffic can go, and under the highway also traffic can go. So that means we are allowing to more traffic on the same space. Likewise, to allow more complex design on a smaller space, we need to have different type of metals. Again, different types of metal never mean some would be aluminum, some would be copper. No, not that. Probably all the metal would be of same type, might be copper, might be aluminum, but one metal stack or the layer will have a dielectric in between, and then we will have another metal. So that means both of them have no connection, no conductivity, and we for sure, if this is our metal 1, then for sure we can run a metal 2 exactly above it without shorting it, because in between we have a dielectric, and that is defined. Define means in process node we have, so our tool also know, so it will never report us any short. Now the thing is that you have a metal 1 like this, perfect, and then you have a metal 2 running like this. Both are not shorting because here we have a dielectric, but we want to connect them. Why we need it? Because probably some blocks are starting from here and some blocks are going here, and we want to connect this block with this block. So metal 1, probably here metal 1s are not available. Not available means metal 1s are used for some other design. So we can't take our metal one from here and do a curve like this and go and join it. We can't do it because it will short. We already have used our metal 1. So that time we need to take the help of our metal 2, this fellow. So I'll just take it like this and I'll connect it. But here, as I said, it is not connected, it is disconnected. In between two we have a dielectric. So to connect them, what we do? We drop a via. Via is this. And via in physical world is actually a drill. What we do, for example, this is metal 1 and this is metal 2 cross section. So to connect this both of them, what we do, we drill a hole here and we insert the conductive material. So we have the this one, like this conductive material, and then metal 2 are passing. So that this way we do the interconnections. And this concept is very important. Many MTech students also don't know about this concept. If you have understand this thing, then let me come to this picture here. So here you can see, as I said in our last lecture, we have how many metal layer? 3, 4, 5 type of metals layer. But we have another special metal layer, and that is this. This is your local interconnect. And local interconnect, as you see here, this is your thickness. Thickness is only 0.1. Scale I don't know, I think nanometer only, probably not nanometer, I think micrometer. So it's 0.1 micrometer. So as thickness is very less, so it will have high resistance. So for sure we can't use Li for running long path. It will be high resistance, there will be high IR drop, so we don't like that. And for power delivery, power delivery, actually most of the metal routing are done for the power delivery. So power delivery need to be have a metal layer which have a lowest resistance possible. So for that we can use M5 for sure, because see M5 how thick it is, more thick, more less resistance, right? Okay. And these are your via, which I said. So if you have your M4 and if you have M5, if you connect with those both of them, you need to use via 4. And likewise, if we have Li here and we wanna connect with M1, we need to use a MCon. Now this is our P substrate. Let me change the color of my pen. Okay, so this is our P substrate. In last class I said, right, anytime you start any layout, the by default canvas you see, it is a P substrate only. So in P substrate we can build a annual here, we can build a diffusion layer here, and to connect this diffusion with our Li, here it is written Li con. In the process node it is called Li con. But whenever we will open it on Magic Tool, we will do it, you will see this is called, we have two different names actually, N diffusion connect and P diffusion connect. So we can say, hey, our Li con is of two type, NDC, N diffusion connect, and P diffusion connect. So in our all of design, we will mostly use Li whenever we doing device level design, like designing our inverter or any gates. Mostly we'll use Li, and if needed we will use M1. So I hope this process design is clear. Now there is something interesting we have in this document. Like again, if I go to design role and if I again go to periphery rules. So in periphery rules there are important things, but you will appreciate it only when we need it. So now I'll open our Magic. Okay, so let's invoke our Magic. So rule of the thumb is that you need to enable grid, snap, and those things. In last video I have shown you how to do it using your command prompt, but you have something else also here. Just go to window and see, here we have the grid. So we can set our grid. So for example, for today, as I said that day also, we need to design our inverter for the schematic we have designed in our previous classes, and which was of 2 micro and 1 micro, 2 micro PMOS and 1 micro of NMOS. So for 1 micro, I think 50 micro grid would be easiest one, and also we need to enable the snap. So for that window, and we can have this one, snap to grid. So you can do anything using command prompt or using this one also. For zoom in, you need to click on press Z, and for zoom out, shift Z. Simple, right? Okay. So now first task is to design a PMOS. So for designing a PMOS, I need to first give my annual area. So I don't know what should be the annual area. So what I'll do, I'll make my annual exactly same as my P diffusion is needed. So right click and I need to zoom 4 because this one is of 0.5, so for 2 micron I need to select how many, 4. So this way 4 and this way 4. Anytime you want to write any command, one way is just bring it forward, and after bringing forward just click here, no colon, nothing is needed, type the command. But if it is not active, this window is not active, probably this window is active, then you don't need to click here and make this window active. You don't need to do that. The simple one is that just press colon, with colon only, like here I press colon, right? This window will become active, but it won't come front. It will be active in background only, and your command will run. But to make things easy for you, let me do one thing. Let me make it always on top. So now we can see this window every time. So for example, I am working something here and then I want to execute some command. So I'll just write colon, and then I'll write what I need to write. I need to paint with NL, and see NL done, right? So okay, so NL is done. Then after NL, what we need to do, we need to define our pdiff. So same box, and again I write colon, and I'll write paint pdiff. And as obvious, we have the DRC error, and DRC error from here only we can see, and those are actually our P diffusion and NL can't be the same. NL need to be little bigger than P diffusions. That last class I said you how to see your DRC, like DRC and then write Y, right? DRC and then Y. But we have another way also, and another way is that just come here in the option menu and come to DRC manager. So in DRC manager, actually you will see all the DRC, any DRC, any number of DRC. For example, these are the boxes where DRC is happening. So for example, if you get confused, there are many DRC and you are not sure which DRC belong to which highlighting, then you just highlight one and click zoom, and see it is saying, hey, this particular area having this. So but we know here is written clearly annual overlap of PDF is less than 0.18 micron, which must be more than 0.18 micro. So let's zoom out and let me make our annual little bigger. DRC gone. So after that, what we need to do, we need to also define our end diffusion area. So there would be some particular rule, like your end diffusion need to have some spacing then annual, but as we don't know, so let us do it. We don't know what's the minimum distance needed. So for us, our end diffusion need to be of 1 micron, right? Which will define the width of our gate, and which is 1 micron for our Cmos. So right click and left click, colon, paint and diff. Oh, we are not getting any DRCs here. That's great. Okay, so now we need to define our gate area here, right? And our gate is of 150 nanometer. So it would be better to fix our grid to something like 150 nanometer we can fix, or 50 nanometer, because 50 nanometer will help us in our further design. So I am changing my grid, and I'll write grid to 50 nanometer and 50 nanometer, and grid got changed. And after grid got changed, I need to select my 3 boxes. So 3 boxes, and I'll go directly here. This one, 3 boxes. Yep, I guess this is, yeah. And we'll write colon paint poly. So poly got installed. Today we don't gonna design a compact, most compact possible inverter. We won't design it because it will take a lot of time, because for designing a compact you need to know all the rules. You need to keep on compacting the design by trial and error method, and then you will be succeed. But for our simplicity, because we are learning it, we will design it little relaxed. But still, here I have given this pdiff and ndiff according to our schematic. See, this vertical is your W, right? And this horizontal here I have already defined is 150. But this drain area and source area is so bigger. And we know from our theory that if drain area and source area is bigger, then it will increase our capacitance. So let me do one thing. I don't know what's the minimum gate area required here. I can know it from our design rule, but as I haven't gone through my design rule, so I don't know. So what I'll do, I will shrink it to something like this much. I want to delete this area. So to delete this area, if you just select it, and now if I press Ctrl D, see, everything got deleted actually. Your pdiff also got deleted, and in beneath pdiff we have the NL. So NL also got deleted, but we wanted to delete only pdiff. So let me do undo, and what I'll do, I will use my command prompt. So I'll colon and I'll write erase and only pdif and then enter. So only PDF got deleted, and see we started getting DRCs, but it's okay. But okay, let me see what DRC is there. So for that, as I told you, we'll go to option, DRC manager. DRC manager already behind the scene is coming, so let me bring it forward. So in DRC manager I'll update, and I'm seeing something. So I'm seeing something, probably I know. So it is written here, P division overhang of PMOS should be, here it is less than 0.25 micro, it should be more than 0.25 micro. And in my last video I said one thing, that in commercial PDK they have diagrams also describing everything, like to help you understand a DRC. And good news is that in Skywater also we have the diagram. I actually discovered it after the last episode. So let me show you how to see this definition in the diagram. So let me bring it here. You just get this code. It is poly.7. This is our code. So here what I'll do, let me make it full. Okay. So here same design rule. This is the main thing. We'll go design rule, and we'll go down, and here, as I said in the beginning, we will go here, periphery rules, and here you see these are the codes. So our code will start with poly. So I'll click on poly, and after going into poly, it was poly 7. So I'll go to poly 7 and see it is here written. Here also it's again ambiguous, probably because only text extension of diff beyond poly minimum drain should be 250 micrometer, right? Minimum drain area, the source area. But to see the diagram, you just need to go down and see here diagrams are there. So you need to find out where is my poly 7. So this is your poly 7, and here sometimes it is ambiguous, but roughly we can see here poly 7 means this area, this is my poly, and this is my diffusion. So this area must be 0.5. So that need to be achieved, otherwise there is a DRC. So let us fix that one. So to fix one, here see we have 1 2 3, that is 150, because one grid is of 50 nanometer. So I will just increase it. Okay, and here before deleting we'll select 5 1 2 3 4 5. So this is the minimum possible design. Actually you can't go beyond this minimum, but as I said, designing a minimum device actually very time taking, because here what I'll do next step, I'll draw LI to create contact. LI will have its different rules, and here the one constraint we have, and that is our grids is of 50 nanometer. I can decrease it to 1 nanometer also, but it will become very clumsy to design. It will become very clumsy. So in actually real world, we design our devices only once, and then we keep on using them again and again. And here also we have some utility which will help you design your inverter as quickly as possible. But as we are engineer, we need to know what behind the scene things are going. So that's why we are designing it manually. So designing it manually and then compact design is little tough for us. So what I'll do, I'll design it little relaxed. So I'll increase our drain area. Don't worry, in our next episode I'll show you the shortcut. But you for sure, I'm doing it manually, right? So you also for sure design it once manually, at least once for a lifetime, and then you can go for the automated route. This manual task will also help you to give confidence in your interview, to tell them, hey, we know how layouts are being drawn from scratch and how the VLSI technology actually working. So please do it. So my PDF is there. So after PDF is there, I need to create a connection. So this is the layers text we had, and as I said, after diffusion, this diffusion could be N diffusion or P diffusion. After this diffusion, to make a contact means a metal layer or something which will communicate with the outer world, or here it is Li for sure. We can use M1 also, no issue. But problem is that if we use M1 directly, skipping Li, then anyway from M1 to diffusion there is no direct path. We need to draw this via, we need to draw this layer, we need to draw this another via, and then again reach to NDiff. So why should do this hard work? So that's why what we do, we always choose Li for now, because we're gonna connect with the silicon area and diffusion area. So okay, so here this Li con could be your NDC, N diffusion contact, or P diffusion contact. So let me draw here our Li first. So I will again select a rough area because I don't know about the rules. Let me select up to this much. Wait, this and then up to this much, and then I'll write colon paint li, and same for this side, paint li. And see, we are having a DRC. You can see this white dots, and this DRC again. Let me bring the DRC manager here, update, and this DRC manager is that here your local interconnection spacing between two slices. Here we have two slices, right? This slice and this slice, between two slices there it should be more than 1.17 micrometer, but here this gate area is 0.15, so that's why it is violating, right? You can also observe this in your same rules. What I shown you, diagram would be there. Okay, you want to see it? Okay, let me go there. This is, we'll make it bigger. We'll go to design rule and we'll go to li. Our code is starting with li, and li I think 03. Yeah, this is li 03. So here it is same. We will come here and see li 03 is this between two slices. This must be 0.17. So see how DRC become easy, like debugging DRC become easy with these pictures. So that's a great thing. Thanks a lot whoever did this hard work for sky130. So let me clean it up. So for cleaning it up, what I'll do, I'll zoom in Z. I'll zoom in, okay, shift Z, and I'll just clean this one box area. So for cleaning, what I can do, one is that control D, but control D has one bad thing, and that is it will also delete all the layer in this box. So in this box, what we have li, we have pdif, we have annual. It will delete everything. Colon, and we'll write erase that particular layer, and which is li. And to keep the symmetry on, we will do the same thing here also. Colon erase li. Okay. Anytime I am doing anything, you keep on focusing here, because here everything is written, whatever things are happening. So this is done here. Here also we need to do the same thing. So let me keep the design symmetry up here. So our division area is up to that for both the things. Here it is up to this. So this is, yeah, this is maintaining the thing. So here also I'll draw my li, but before that let me connect it here. What is happening here, see, you have the diffusion and you have the li, but they are not interconnected because in between we have a dielectric. To connect them, we need to draw a hole or drill, and how to do it, we will use a L icon, and L icon is different for your PDIF and NDIF. For PDIF it is PDC, for NDIF it is NDC. So we'll draw a NDC here. So I don't know about the area, but roughly select something like this. For sure it need to have some overlap, I guess, so I'm giving some space below and side, and select here, and I'll write paint PDC. And after paint PDC, see, we are having some errors here. So I'll go to my DRC window, which is behind the scene. I'll update it, and this is the error. Okay, yeah, you see it, right? We can increase it to see the full error code, or I can increase it here. So error code is our li5. Okay, and it is maybe clear or may not be clear. So we'll again go to our rules book, and in rules book we'll go to design rules. Okay, and it is li. So here it is our li5, right? And in li5, if I go down and see, this is your, and here it is saying that this side and this side, it need to be 0.08 micrometer. So see here what is happening actually, if you can see it, let me zoom it. Yeah, one grid is of 0.5, and this is your that PDC. This PDC and your diffusion is ending here, but after PDC the diffusion area must be of 0.8, and our grid is of 0.5, so that's why we are having the error. So let me increase the diffusion area. So what I'll do, I need to have zoom. I will increase it here, from here up to here, because this side also I'll have the same issue, and I'll just paint PDIF, paint PDIF. Okay, and after doing it, still DRC is there because our LI also need to be modified. So I'll select this LI and DRC is gone. So now what I'll do, I can do everything here this side also, but it is symmetrical. So what I'll do, I will copy it, and not single layer, I want to copy all the layer, right? So to copy all the layer, first what you need to do, you need to define your box and then press A on your keyboard. So A will select everything, and then to copy, don't do anything, just bring your cursor wherever you want to copy it, like the lowest most x and y coordinates. So it should come here, right? This is the lowest most x and y coordinate. I brought my cursor here roughly, and then type C on your keyboard, and magic, it came here. And we have no DRC. That's a very good news. We will do the same thing below also. So now what we need to do, we need to create the body connect, because it have our 3 terminals, but we need to have the body connect, right? And for body connect, like for PMOS, as we know in general, this is our PMOS. So in PMOS we have the N well, so we need to have a N plus region to reduce the resistance, and then we will use the connection to LI or M1. We will do that, right? So let me do in general. So I'll just select area, and I will say paint paint and diff. But you can see we are having some DRC. Why this DRC? There should not be any DRC, but we are having a DRC, and DRC is saying that N diffusion spacing to N well. If you go in your rulebook, you will find the exact meaning, but I know, let me tell you, it is actually telling us you can't draw a N diffusion inside a N well. There should be a gap between N well and N diffusion, right? So how to do that? So for that, actually we have a special layer here for creating the body connect, and body connect is also called tap, creating a tap. So for creating a tap, we need to use a different layer. That layer will be an N plus layer only. To not to confuse our tool, they have decided to go with some different layer, but in fabrication probably it will be the same layer as NDiff only. So don't get confused. So let me do U, and let me type paint and tap, and ntap is there. After having ntap, what I need to do, you have the ntap. Ntap is nothing but your N diffusion only. Then to create a connect, you need to draw your LI, right? And after that, what I need to do, I need to actually create my connection, right? So here again, we have a separate type of connection, or the separate type of via, which is LI con only, right? Like connection between LI and the silicon substrate, and that is called your N substrate connection. Or in simple, you can just write paint N tap connection for C, N tap connection, so N tap C. Just write this. This is the shortcut actually. Where it went? Yeah. So we have this. Now you can see we have some DRCs here. So if I go there, and in DRC it is saying me, if I just extend it, it is the same error we got during creating this connection, and that is that your LI must be around overlap should be around 0.08. So one option is that, hey, increase the LI area. Another option is, hey, reduce the this via area, LI con area, or this ntap C area. So I'll do U. Let me do U, and let me zoom in, actually go up, and here I will select a smaller area like this, to avoid the DRC, this area, and then I'll write colon paint and tap C. And great thing, I think there is no DRC now, it is DRC clean. So great thing. But one thing here, in physical world, what we do, we don't only draw one connection. Here one connection is means a bigger hole will create, but in general we don't do that. What we do, we instead of a big via, we insert few small via here, like 3 small via, but for now it's okay, let it be. We need to do the same thing going down also here. So this area is your P area, paint, this will be a P tap, okay, paint P tap, and then paint Li, and then I need to use my connection, but we know that our connection need to have some overlapping area, so I'll select roughly area and I'll write paint, so it would be P tap C, P tip connection, but I think we have some error, so I need to increase my, okay, so if I increase there would be a different error, but let me do it, paint P tap, yeah, so but we are having a different error, and the different error is that your poly spacing, right, your poly spacing and diffusion tab should be this. So what we'll do, we will just select everything here, so I'll just select, so for selecting everything, create the box and then press A, so everything got selected, and then we need to move it down, right? So for that there are different type of method we can use. Let me try one here, move and then down, and then by one grid, and yeah, correct. So we are able to move everything by one, and I think our DRC is also removed, and see there is no DRC, there is still one DRC is there, poly spacing, so we need to move this thing further down. So again, let me create the box, press A in your keyboard, select everything, and then come here and write move down by another one, and perfect, and then update. And in our good news, and yeah, good news, there is no DRC, but to see the whole layout in once, there is a shortcut, and that shortcut is V for victory, V for victory, okay, so press V in your keyboard and you can see whole layout in once, V for victory, and we can see everything got created. Now there is a important concept we need to know. So now our inverter is fully ready. Actually, we have the 4 terminal for PMOS, we have the 4 terminal for NMOS, but we need to do the routings, and we can do the routings, but there is a very important concept we need to know. Anytime we work on industry, we don't do routing anywhere, like, okay, let me connect this to that and that to that. No, actually we most of the time we need to follow a grid pattern or a guide pattern. Yeah, things won't be clear to you currently, but it's okay. In our next video for sure we'll go through deep into those things, how to connect this thing, create input output, create the level, do the simulations, and probably we'll go to LVS and then the final result. But before that, you please do it and comment down and let me know you are here, and I'll bring the next video very soon. Till the time, keep helping, keep smiling, and keep doing these projects. Till then, tata, bye bye.